Good afternoon, everyone. I hope I am audible. So, welcome to this webinar focusing on techno-commercial impacts of distributed solar generation. My name is Deepak. I'm with the Energy Program of the World Resources Institute. This webinar is part of the Sustainable Energy Transformation Tamil Nadu initiative, which aims to facilitate the higher clean energy deployment in the state by working with different stakeholders to find sustainable and equitable. Okay, is my voice clearer now? I see that there is a comment that it's not clear. So if it is clearer, please do type it. Otherwise, I'll assume that it is fine. Okay, so as I was saying that it's part of the Sustainable Energy Transformation Tamil Nadu initiative, which aims to facilitate higher deployment of clean energy in the state by working with different stakeholders across sectors. So, for instance, the DISCOM, the agriculture department, wherever clean energy interventions are possible, this initiative aims to work with those departments across the state and try to increase the clean energy deployment. This webinar will be presented by my colleagues at Auroville Consulting, Martin Schurfler, who is the co-founder of AVC, and Reshma Suresh and Victor Katrib, who are renewable energy experts with AVC. Before I hand it over to Martin, a few points to note for the audience. One is that the report is available at aurovilleconsulting.com. You could download it from there. Today's webinar will follow the format of a presentation for 45 minutes, followed by 15 minutes of Q&A. We will be monitoring the chat window, so please do type in your questions in the Q&A segment. And if you do have any issues related to audio or any other problem, please do type it in the chat. We will try to help you out on that. So with this, I'll hand it over to Martin to get us started. Thank you. Martin, you're on mute.
Before my two colleagues, Victor and Reshma, go into presenting the findings, I wanted to quickly present a little bit the context with which we worked and the overall objectives of this exercise. And I think one good way of describing what we were attempting to do is that we looked at a distribution network as an energy island. So an energy island that remains connected to the larger grid, draws grid services from there, but also provides services to the larger grid. The objective was to explore what it takes to develop an energy neutral or positive distribution network by introducing solar energy, time of the day tariffs, and consequently distributed energy storage. By energy positive or neutral, we mean that 100% of the annual electricity requirement comes, in this case, from distributed solar energy. In this context also, the way we have defined solar energy penetration was in energy terms. That means on the consumption and not in capacity terms, which is different than most of the organizations would have defined it. We have done this because we found this a more challenging proposition and also a more exciting proposition and relevant in the context of exploring a transition to 100% carbon neutral electricity grid with a very strong presence of distributed generation resources. For the simulation, which will be presented by Reshma and Victor, we have basically taken two approaches. One is simulation on the HD feeder level, where we have introduced ground-mounted utility-scale solar. And the second one was a simulation at the LT feeder level, downstream a single distribution transformer, where we have introduced behind-the-meter solar energy system. I think one objective also was to demonstrate the benefits of producing solar energy close to the point of consumption to leverage on the existing distribution infrastructure. So in our simulation, we have connected, for example, the utilities solar systems to the existing feeders, which is also different than the approach that is being currently promoted in India. If you, for example, look at Kusume scheme, where a dedicated evacuation infrastructure is required. The aim finally is to show the technical and the commercial benefits of this approach, which means reduction in T&D losses, but also reduction in cost of supply and higher revenue for the utility. The analysis was undertaken for 10 feeders at the substation in a road in Tamil Nadu, and for a single LT feeder connected to the same substation. For the purpose of today's session, we needed to reduce the complexity, and we will present findings for 2 HT feeders and findings for the single LT feeder. If somebody wants to download and read the report, you can see the link at this slide that is open right now. Okay, a little bit to the content for today. A very quick introduction and context setting. Then a little bit about the methodology that was used in this simulation, a background on the road substation, and then the main focus will be on the results, both the technical and the commercials. A little bit of recommendations of how could some of the findings be taken up in terms of regulations or policy making. And finally, we would like to close with the Q&A, which will be facilitated by Deepak. So on the introduction, next slide. And this is most likely familiar with all of you, so I will not dwell on this too long, but we know that India has a target for renewable energy of 175 gigawatt capacity to be achieved by 2020, which contains a separate target or a sub-target, so to say, of 100 gigawatt of solar energy. India has also made a commitment under the Paris Agreement to have 40% of its installed generation capacity from non-fossil fuel by 2030. As of January 2020, we had 86 gigawatt of installed capacity of renewable capacity, and a growth from 2019 to 2020 of a recapacity of about 9.46%. If we look at Tamil Nadu released its solar energy policy in 2019, which has set a solar energy target of 9,000 megawatts to be achieved by 2023. What is slightly unique for Tamil Nadu is that there is 2 sub-targets. One is a 60% of what has been termed has to come from utility category solar, which is basically solar systems with the primary purpose of sales of electricity, and they are under gross metering. And 40% of this 9,000 megawatt target is supposed to come from consumer category solar, which is behind the meter solar, which has a net feed-in mechanism in Tamil Nadu. And important to notice, with a very low net feed-in tariff. The current net feed-in tariff for the surplus solar is at 2.28 rupees per kilowatt hour. So if we look at what has been achieved so far, as of March 2020, we had a cumulative 3,960 megawatt of solar energy installed. The majority of it goes on account of utility category solar with about 3,756 and a very moderate amount of consumer category rooftop solar, which currently stands at 156 megawatt, which is less than 4% than the target that I've mentioned earlier of the 40% or 3,600 megawatts. So there's a long way to go for the state if it wants to achieve its consumer category solar target. Yeah, and at this point, I hand over to my colleague, Victor, to elaborate on the methodology.
Good afternoon, everyone. As Martin said, my name is Victor. I will introduce the methodology we took for this report. First step we took was the collection of raw data from a road substation. We had to go there in person, collect data from logbooks, was like manually entered by the workers there. And then we had to manually enter the data in Excel. Second step was the data processing, where we use Python and Excel, statistical tools, some Python package to organize the data better and to be able to perform the simulations using OpenDSX on the step number 3. After performing the simulations, we move to step 4, which is the technical financial analysis. On the next slide. Okay, so step number 4, for the report, we analyze 8 scenarios, but for the sake of this presentation, we are analyzing only 6 scenarios, which are business as usual scenario, which is the current scenario without any intervention, 40% solar penetration, then 70% solar penetration, 100% solar penetration. Then we add time of the day tariffs on top of the 100% solar penetration. And finally, we come up with a scenario of 100 solar penetration, time of the day tariffs, and storage. In terms of results, we analyze the active power flow, voltage profile, and the violations, distribution losses, feeder line capacity, and reactive power support. On the financial analysis, we analyze the reduction in cost of supply, increasing revenue for the utility, net revenue, which is basically billing collection minus cost of supply. And then we compare to the business as usual scenario, like evaluating each scenario individually. Also, like we do the same analysis for utility category and also consumer category. On the methodology, a few considerations before we move on. Migration to a lower tariff slab is not considered, especially for domestic consumers, meaning that when solar energy is introduced, because of self-consumption, probably that's less energy coming from the utility, which may incur in a change of slab. This is not taken into consideration in our report, otherwise complexity will increase substantially. Demand charges are also included in the average billing rate. Growth in the energy consumption is not considered since most of our analysis is done on a yearly basis. So growth in the energy was not considered. Distribution and network upgrades costs are also not considered when we analyze the final savings and compared to the business as usual scenario. Like this upgrade can be change, replacement of transformers, adjusting set points of voltage, and etc. As Martin said before, solar penetration is defined in terms of energy, not in terms of capacity. This will be explained further by my colleague Rashma in the further slides. In terms of, so for the utility, we did not consider any diurnal price variation since this data is not publicly available, meaning we use an average power purchase cost for the whole day. And we use this average power purchase cost for calculating the cost of supply as well. When analyzing the feeders data, we remove all the grid outages, meaning we analyze solely the profile of consumption. We remove all valleys and spikes in the load curves. Reduction and increase in transmission losses are not considered. As Martin mentioned before, we analyze the substation as an island. And also because our data was mostly hourly based, we did not perform any transient analysis, meaning harmonics and frequency were not part of the scope of this report. Now I'll forward the word to my colleague Rashma, which will do an introduction on the analysis of the data from the Erode substation and the data we collected. Rashma?
Thank you, Victor. I will continue with the Erode substation. Do I have the remote controls?
Yes, you do.
Okay, no, I couldn't change the slide.
A second.
Sorry.
Yeah.
Okay. Sorry.
Taking your control?
No, I couldn't.
Right.
Sorry.
Try Rashid.
Yeah, I couldn't. Thank you, Victor.
Okay.
Okay. So yeah, thank you, Victor. So I'll be continuing with the E-road substation. I'm just switching off my video for better connectivity. So yeah, so as Victor said, we have collected 1 year, that is hourly data from E-road substation of the year 2018, and the E-road substation is located in Tamil Nadu. You can see the details of the substation. It has 10 feeders and it is a 110 power 22 kV substation with an annual energy consumption of 340.12 million units. Okay. Sorry. Why the slide is not moving?
Martin, Victor, if I may suggest, it would be good if you could move the slides while Reshma speaks through, and then she can.
Yeah, I could move it now. Thank you.
Okay.
Thank you. Okay. Sorry for the interruption. So yeah, I will continue with the consumer profile. So you can see that the total number of consumers or the service connections in different consumer categories for both E-road substation and DT under consideration. So we have selected DT26 of collectorate feeder as it is having a similar percentage contribution as that of E-road substation for different type of consumers, that is residential, commercial, industrial, and others. So you can note that a high percent of the total consumers, that is almost 2/3 of the consumers of the total, are under residential category for both E-road substation and the DT26 of collectorate feeder under consideration. So you can see the percentage distribution and the total numbers here. Okay. Then coming to the schematic diagram. So as Martin said before, for the utility category solar, we have aggregated all the consumer at the tail end of the feeder, and we have PV plants connected near to the consumer load. So whatever solar energy is produced, it will first serve by the consumer near to the PV plants, and if there is any surplus solar, it will go back to the substation and beyond. And for the utility category, we have rooftop solar, and after self-consumption, if there is any excess power, if there is any surplus energy, it will go to the DT network and it will serve the nearby loads. And then if the surplus is still exists, it will go to the nearby DTs. Coming to the solar capacity, as I said before, the annual energy consumption for all the 10 feeders is around 340.12 million units. So here we have designed the solar capacity based on each feeder's annual energy consumption. So to have 100% penetration, we should install around 214.69 megawatt of solar capacity, which is around 214.69% of the total feeder capacity. So here the total feeder capacity is 100 megawatt. That means 10 feeders with 10 megawatt maximum capacity. So it will have a total of 340 million units. So then now you may be wondering, how is it possible? So it is possible with a properly planned storage system and demand side management that we can discuss in detail in the coming slides. So moving to the consumer category solar, we have the same situation here. For 100% penetration, we need to connect 398.52 kilowatt of solar, which is around 221% of the total DT capacity. So here for the consumer category solar, we have standardized the solar capacity for the 3 consumer categories, that is 3 kilowatt for residential category, 10 kilowatt for commercial category, and 25 kilowatt for industrial category. So depending on the penetration level, number of consumer solarized will vary. So now, sorry. Okay, now we will move on to the result analysis of both utility category and consumer category. So please note that we have done the steady state power flow analysis for 1 year hourly data using OpenDSS software, which is developed by EPRI for all the scenarios under consideration. So for the purpose of the webinar, as Victor said, we will first discuss on the business as usual case, and then we will introduce solar at 3 different penetration level, that is 40, 70 and 100. And then we will introduce the time of the day tariff to 100% penetration level, and then we will introduce storage to 100% penetration level. So first we will discuss the technical analysis, and then we will move to the financial analysis. Okay. So the first in the first result analysis, you can see the feeder capacity overloading. So as I said before, the maximum feeder power carrying capacity is calculated as 10 megawatt for all the feeders, and since the penetration level was fixed, according to each feeder's annual energy consumption, the amount of solar capacity connected to each feeder will differ. So let us see which all feeder can go up to 100% penetration level. So here you can see Erode Town, Solar feeder and Surampatti feeder. 3 feeder can go up to 100% penetration level, and for 2 feeders there is no overloading up to 70% penetration level, and for remaining 5 feeders they can go only up to 40% penetration level. So now we will see how this will change with the incorporation of different strategies. And as we have time constraint, we are going to discuss only 2 feeders, that is Karunkalpalayam feeder and Market feeder, which is firstly affected for the utility category. So now we will discuss the active power flow for the Karunkalpalayam feeder. So here you can see that under BAU scenario, that is business as usual scenario, how the energy, the power is flowing from the substation, and we are showing a 24-hour, that is a single day power flow. As we have limitations, we couldn't show the whole year data. So with the introduction of 40% penetration, you can see that during solar hours, there is surplus solar energy which is flowing back to the substation, and with the increase in penetration, you can see here how the power that is flowing from the substation or the net power changes with increase in penetration, that you can see here. So with 100% penetration, the surplus will increases. So now we will introduce the time of the day tariff, meaning it has a high tariff during peak demand hours. So what we have considered is a percentage of load during that hour will be shifted to the solar hour. Thereby we will increase the local consumption. So now let us see how the effect is happening. So, you can see there is a small reduction in the energy, that is the power that is flowing back to the substation. Now let us see with the introduction of storage how it will affect the active power flow. So here please note that we are charging the battery during surplus solar hours, and we are discharging it during night hours And here you notice that it is less dependent on the power that is coming from the substation, meaning we are depending more on the local solar generation and storage. Okay. Now here next we can see what is the impact of storage on the peak power that is flowing through the feeder over the year. So here you can see that at 40%, 70 and 100%, what is the peak power that is flowing through the feeder. So here you can see that for 70 and 100% penetration, it is violating the maximum 10 megawatt capacity. So for both Keringalpalayam feeder and market feeder, 70 and 100% penetration is not a feasible solution without any other strategies. So what we have done is we have sized a storage system that could store up to 100% of the total surplus solar energy. So for Keringalpalayam feeder, the capacity is around 95 megawatt hour, and market feeder it is around 102 megawatt hour. Now we can see how it will impact on the peak power that is flowing through the feeder. So here you can see that for both the feeders, the maximum or the peak power is below the maximum feeder capacity of 10 megawatt. So that means 100% penetration with a properly planned storage system can take the 100% penetration level without violating the feeder capacity. So now we will discuss the distribution laws. So for here you can see the distribution laws for Keringalpalayam feeder and market feeder. So for Keringalpalayam feeder, this is the around 18% is the distribution loss for BAU scenario, and with the introduction of solar, you can see a decrease in distribution loss, and with increase in penetration, the distribution loss will proportionally increases as there is more energy flow within the network. And with the introduction of storage, the net energy flow will be less, and which will have a very good impact on the distribution loss as well. We could reduce the distribution loss even less than that of BAU scenario. Now we will see the utility category voltage profile for a single day for Keringalpalayam feeder, which is the worst affected feeder. So please note that the minimum and maximum allowed grid supply voltage can go, like according to TNRC, it can have 10%, it can go up to 10% below the rated value, and it can go 6% above the rated value. I have shown the limit as red color. So let us see what is happening for the BAU scenario, what we have observed for BAU scenario. So here you can see that for most of the hours for Keringalpalayam feeder, it is violating the acceptable limit. It is having a very low voltage profile, and we can see with the introduction of solar, we can see an improvement in voltage profile. So here you can see that with 40% penetration, there is an improvement in voltage profile, and with increase in penetration, especially during solar hours, the voltage will be shifted more to the upper voltage ranges. And this you can see here. So with different strategies or different levels, how the voltage is varying, you can notice here. And here you can observe that even with non-solar hours, there is improvement in voltage profile as we are making use of the smart inverter capabilities of the solar inverter. So with a proper reactive power support, we could improve the voltage profile even during night hours as well. And now we can see with the introduction of storage, how the voltage profile is changing. So you can notice that the fluctuation between upper voltage range and lower voltage range has come down, and we have an improved voltage profile with the help of storage, as we are more depending on the local generation and storage system. Now we will see here we have the utility category voltage violations. So what this slide talk about is the percentage of voltage violation that is happening for Karingalpalayam and market feeder. As I said before, we have done the analysis with 1 year hourly data. So there is around 8760 data points. So for how many data points the voltage is violating? So we have that is whether it is going below 100% of the rated value, or whether it is above 6% of the rated value. So here we are showing it in the percentage of the total hours. So as you can see here, for Karingalpalayam feeder, what we have observed is around 87% of the time the voltage is violating. And with the introduction of solar and different strategies, that is TOD and storage, we could drastically reduce the voltage violation for the whole year. So same is the case with market feeder, so that you can see here. So with storage, we could bring most of the voltage at different like tail end voltage to within the acceptable limit. Now we will move on to the consumer category result analysis. So here we have around 236 consumers, and the number of consumers all rise increases with increase in penetration. We have already discussed the details of the solar capacity for different consumer category. So now we will see the power flow from beyond DT26 under consideration. So for business as usual scenario, you can see how much power is flowing from the substation to the DT26 and to the loads. So you can see here. So now we can observe what is happening with introduction of 40%, 70 and 100% penetration level. So you can see that with 40% solar, there is a reduction in power that is coming from beyond the beyond DT26, and we are less dependent on the power that is coming from beyond DT26 during solar hours. And with increase in solar penetration, we could see more energy is flowing back to the DT26 and to the nearby DTs. And with increase in penetration, this will further increase. And now we will introduce the time of the day tariff as similar to that of utility category. So here you can see the effect of that. There is a reduction in the energy that is flowing back to the DT26 to the nearby loads, as we are having more local consumption. So now with introduction of storage, we will be more depending on the local generation, and it is less dependent on the power that is coming from beyond DT26. So coming to the distribution loss in consumer category, here you can see that with increase in penetration, there is an increase in distribution losses. That is a proportional increase in distribution losses. That is mainly because because the net energy flow within the network is increasing with increase in penetration, and with a proper planned storage system, we could reduce the distribution losses than the BAU scenario. So next we will see different voltage level, the consumer category voltage at different service connection point. So here you can see the percentage of service connection points at different voltage ranges for two time frames. The first one is during solar hours and the other one is during night hours. So for BAU scenario, you can observe that most of the service connection point are in low voltage ranges. With increase in penetration, most of them are in upper voltage ranges, especially during solar hours. So here you can observe that. And here there is a little red color, means there is a violation. So this you can observe. So with introduction of storage, but we can see that many of the voltage, like there is an increase in percentage of the service connection point in the middle range of voltage, that is 0.98 to 1.02 per unit. That is an ideal case. So during night hours, you can see that here as well for BAU scenario, the voltage is mostly in the lower range, and with increase in penetration, how it is changing. So in most of the case, the voltage is with in the lower range as well, that is below 0.98 per unit. And with increase in penetration, you can see that most of the voltage at service connection points are in the range of 0.98 to 1.02 per unit. So that means we can have a better voltage profile with the introduction of 100% solar and storage. So coming to the feeder capacity, the LT line capacity for this DT26 under consideration. Here you can see that, okay. So here all are in blue colors, and if there is any red color, means there is overloading of the line, and the thickness of the blue line shows the current, there is an increase in current flow. So with 70% penetration, you can see that the thickness is increasing here. That means more current is flowing through that lines. And with 100% penetration, you can see there is violation here. And with introduction of TOD, we couldn't reduce the violation. So still there is violation here. But with storage, you can see there is no violation. That is, the feeder can take the 100% penetration without violating the feeder capacity with a properly planned storage system. So on concluding the technical analysis, we can say that 100% penetration is a winning proposition with a properly planned storage system and demand side management. Also, based on feeders energy consumption, we can go up to 100% penetration level without violating the feeder capacity. So now we'll move to the financial analysis, and Victor will continue. Thank you.
Thanks a lot, Rashma. I'll take on from now with the financial analysis. We're gonna do a quick summary on the Carangal-Palhan feeder for 1 year. In terms of total unit supplies, which means units supplied from the grid and solar energy and storage when it's the case, we have an increase in total units supplied with increasing solar penetration. However, when we introduce storage, the amount of energy supplied go back to slightly what was the business as usual scenario due to a better management of the and storage of the excess solar energy. In terms of cost of supply, it also it decreased under 40% solar penetration and 70% solar penetration, but increases back under 100% solar penetration and with storage. Again, when solar plus storage is introduced, we go back to the same levels as the business as usual scenario. In terms of average cost of supply per unity, it's just a simple division by the total cost of supply. per unit supplied, we can see that there's a reduction in all solar penetration scenarios compared to the business as usual scenario. When solar plus storage is introduced, the average cost of supply increased slightly, but it's still below the business as usual scenario. In terms of revenue, just a quick parenthesis, when we talk about revenue, we're talking about billing collection from the utility. Revenue increases with each solar penetration scenario, but also decreases compared to the 100% solar penetration when compared to the 100% solar penetration plus storage scenario. When we analyze the net revenue, which is simply the revenue collected minus the total cost of supply, we can see there are savings for the utility on the 40% solar penetration, 70% solar penetration, and even 100% solar penetration scenario. However, financially, the best proposition is the 100% solar penetration plus TOD plus storage. Two things I'd like to highlight here is that even though the average cost of supply is higher under 100% solar penetration plus storage, we still have a better financial result because we are supplying less units to the grid. And also another thing that I'd like to highlight is that the utility runs in a loss. So the objective of this exercise is to minimize the loss. So for business as usual scenario, we have a 15.66 crore loss for the utility, but a loss of 5.91, which is like substantial savings for the utility. When we compare the savings over 1 year compared to the business as usual scenario, for the Carangal-Palhan feeder, we have the best result under 100% storage plus TOD, and also like at 40% solar penetration is a similar result. For the market feeder, however, we have the best financial result at 100% solar penetration, and storage, but also at 70% solar penetration. So that's just slightly different. So for Carangal-Palhan feeder, we have the best optimal scenario in terms of just solar penetration at 40%, but at market feeder at 70% solar penetration. But the best scenario for both cases is still 100% solar penetration plus time of the day tariffs plus storage. Another exercise performed for this report is the financial analysis over 25 years. So we introduced a 6.97 solar plus storage tariff over 25 years. We got this value from the SECI tender from August 2019. And for Carangal-Palhan feeder, we have savings of almost 100% and a break-even year 12. So a net revenue over 25 years of 0.04 crore loss. However, for market feeder, we actually have a profit over 25 years. Savings of course, 104% and a break-even at year 7. I would like to highlight that under business as usual scenario, the utility will never profit if any strategy is implemented. So we can see that the implementation of solar plus storage is either technically very good for the utility, but also financially very good. We will do the analysis now for consumer category. We're going to analyze the same parameters as we analyzed for the utility category. We can see that slightly different results when we talk about 100% solar penetration plus time of the day tariffs plus storage. We have a loss of 0.06 crore with 100% solar penetration storage, which is still better than the business as usual scenario of 0.14 crore loss. However, for a commercial category, we have an increase of financial results, better financial results with increasing solar penetration. And this can be by the fact that, as Martin pointed out before, the net feed-in tariff is very low. So that means that utilities purchasing power at a very low cost. So the increase in solar penetration is financially attractive to the utility. Another thing that makes the analysis a bit difficult is that we do not have any solar plus storage tariff in place. So for this exercise, we estimated at 8 rupees per kilowatt hour solar plus storage tariff, which is slightly high. We perform also a similar exercise for the utility category over 25 years for the consumer category, and we had financial savings over 93%. Just to highlight, this is 100% solar penetration plus downloaded tariffs plus storage. So we had savings of 93%, meaning that there's still a loss, but the loss over 25 years is almost minimized. So you can see like the graphs in blue and red, meaning like blue is the savings to utility and red is the loss for the utility. So over time, the utility start profiting around year 13 to 14, and the areas of the graph are almost the same, but the area in red is slightly bigger. We will move on to the key findings quickly as we are running out of time. So the key findings are a combination of both financial and technical results. So the key findings we have is distributed solar energy improves voltage profiles and also reduces distribution losses, and is an opportunity for to improve voltage service levels. So our recommendation regarding these key findings is regulators to impose measures to implement voltage service standard. As of now, Tamil Nadu has no penalty for utility providing a low voltage, and we also recommend that this voltage service level increase to plus or minus 6%, which is the recommendation of Central Electricity Authority. In terms of existing infrastructure, the existing infrastructure in Tamil Nadu is able to take up high levels of solar penetrations. In terms of recommendations, we would like to recommend conducting feeder-wise solar energy hosting studies, ensure data is up to date and easily accessible, accelerate real-time metering at feeder level and DT level, deploying equipments to automatic regulate voltage, and publish maps and make maps that show the available grid interconnection points with optimal solar energy points, identify feeders with low average tail-end voltage as Kurangau-Palian feeders, Rashmus had showed before, and also make data public available. Basically, we're trying to say with this recommendation is to make data more reliable and easy of access, so the utility itself or other players can conduct more studies and show the optimum feeders and DTs to prioritize for solarization. And the last key findings we'd like to point out is that time of the day tariffs facilitate higher local consumption of solar energy, reduce distribution losses, and increasing revenue. Also, 100% solar penetration has been proven to be a winning proposition, technically and financially, especially for utility category solar, and also solar energy can be a good strategy for cost of supply reduction for Tangential. So we recommend introducing time of the day tariffs for all consumers, not just high HT consumers, as also for low tension consumers. As of now, just high HT consumers have time of the day tariffs. We also recommend launching pilot projects that integrate solar energy and storage. So in a way, we can have real data to be analyzed, not just simulations, and also introduce solar plus storage tariffs for both utility and consumer categories. So this way, solar plus storage strategies can start to be deployed and incentivized by the utility and government. Thanks a lot. I'll pass the word to Deepak now for Q&A. And thanks a lot for your time.
So thank you, Martin, Reshma, and Victor. It was a great presentation, and we already see that there are about 10 questions already which are lined up, and I'll be asking them sequentially. But at the same time, there are also questions which I have attempted to answer through text, especially questions sought by Ms. Susmita Subada and Mr. Michael. So hopefully you are happy with those answers. If not, we could try and take them up depending on the time available. So I'll start with a question by Mr. Abdul Qadir. So any specific reason on selecting the Erode substation for the studies?
Yeah, maybe I can answer this. Abdul, glad that you are here. To be honest, no particular reason. Erode substation was the only substation where we were able to get data. We would have been quite happy to do a second substation, but it so happened that this was the only substation where we were actually able to get data. Therefore, Erode substation. That's the only reason.
And then we have, thanks Martin, we have a question from Ms. Akila. So are the results of all the feeders that you have studied available in the, along with the report, are the results of all the feeders also available in the report?
Yeah, yes.
Okay. Okay, then there is a question which was asked by both Ms. Akila and Ms. Subhada about a storage system. So what is the storage system that has been considered, and what is the sizing of the system?
Reshma, would you like to answer this?
Yeah, the sizing of the storage system, we have sized it in order to store 100% of the surplus solar energy, and we have used the model which is available in the OpenDSS software. So it is not any any particular system. We have used the one which is available in the software.
Just maybe to, we have used lithium ion, of course, as technology. And Victor is just scrolling back to one slide where we have shown the storage capacities for the two selected feeders that were introduced.
Yeah.
Yeah. So here you may see that for the first feeder, it was a storage capacity of 95 megawatt hours. And for the market feeder, the second one, we had a capacity of 102 megawatt hours.
Okay. I think this also answers a question which Mr. Arun Kumar Vijayan had asked in the chat window. So, great. So then moving on to one other question from Mr. Abdul Qadir. What do you mean by 100% plus TOD scenario? If he's requested that we explain what that implies.
Yes, what we mean by 100% plus solar penetration plus TOD is like we take the actual load from that we got from the substation, we implement, and then we introduce time of the day tariffs under the actual load. Is an exercise because time of the day tariffs are not in place for this particular load. So after we implement the time of the day tariff, which is like a higher tariff on the peak hours from 6 to 9 in the morning and 6 to 9 at night. So we modify the load shape, and then we introduce the 100% solar penetration after modifying the load shape. Thus, I hope this answers the question.
Right. So there is a related question from Mr. Michael asking whether it is possible to reach this 100% penetration along with TOD and storage at once. His view is that it could be a challenge, especially if this is the only combination without violation. So is it actually possible to get this in a real time, or is it more of a simulated results, which is an ideal scenario?
Well, maybe Reshma, you may want to come in after that, but I guess the objective of this presentation actually was to highlight that this is possible both technically and of course has substantial financial benefits to the utility with the assumptions, of course, that went into this work. But yes, so based on the simulation that we have undertaken, 100% solar energy penetration in energy terms is possible, provided that you have the additional two strategies implemented, which are the time of the day tariffs and the energy storage.
To add on?
I hope that answers this question. Yeah.
Also, according to our studies, a few feeders can take 100% solar penetration without storage. That is important to highlight as well.
Okay. So, Reshma, you want to add on? Please come in.
Hello, is it audible?
Yeah. Yes.
Yes.
Yeah. So yeah, as we have analyzed, and in erode substation, we could analyze different type of feeders, with lower consumption and with higher consumption as well. So yeah, it is a simulation study with actual data, and this is a steady state analysis, and yeah, there will be other challenges and power quality issues as well. So that is why we are recommending a pilot project, so that we can have the analysis with a practical system. So that's it. Yeah, thank you.
Thanks, Reshma. And then two more follow-up questions from Mr. Michael. We can take them since we have about 2 to 3 minutes left. One is, he wants to know, Victor, you mentioned that this solar plus storage tariff is slightly higher at 8 rupees per unit. So what is the reference point with which you are saying it is higher? So that's his question, number one.
I didn't get the
Feed-in tariff. So consumer category solar.
Okay. So for consumer category solar, the tariff is just a high level assumption. Like for consumer category, there is no tariff in place. So it's just an assumption we did. For the report, there's a sensitivity analysis where we explore the effects of different tariffs from 4 rupees up to 11.61. So we have a more broad analysis. But for the presentation, we just took a middle one between 4 and 11.61. So yeah, it's just a high level assumption, but differently from utility category where we actually have tariffs that have been tendered.
So, and then one other question which he has is, which particular technology within the lithium ion series have you considered? So my assumption is that you haven't dived down deep into the chemistry of it. It's more of a mathematical thing, but yeah, and capital cost assumptions, I think, are there in the study. So Mr. Michael, you could take a look at the study once you're done.
You have answered it, Deepak. So yeah, we didn't dive into the chemistry. Yeah.
Okay. And I think the last question that we'll take for today is, I'll combine both Mr. Abdul Kader and Mr. Ram Arvind's question is, is it too early to discuss storage as a solution to Tamil Nadu, and is it feasible for the consumer scale?
Well, I guess this is a bit giving different opinions. And just to counter, I think it's actually too late, not too early. And even if you look at most of the houses in the state and in India already have a UPS, right? So, but what we don't have yet is basically a battery, even whether it's a home system or a commercial system, that is grid interactive both ways. So there must be millions of UPS systems already in place. So definitely, and of course it's because of the poor power supply quality, but it seems that the consumers are willing to spend on reliable power supply, including storage already. So the next step is actually a small one. The next step is that the same storage system is grid interactive.
Thanks, Martin. And then before I just begin to close the session, there are 2 more questions which I think can also quickly address. One, have maintenance costs been considered in the modeling, let's say over the time period of the particular project? Have you also considered the O&M requirements for the storage system?
Yeah, so we have basically used the levelized cost for the systems, and the levelized cost does include O&M costs. Yeah, they have been considered.
Sure. And then the last one for today from Mr. Shatrughan is, what was the total project cost and who funded? So again, my answer to that is this is a simulation study, and it's not an actual implementation on ground. So I think we hope that TANGETCO would see the benefit of the studies that we've done and take an implementation forward. Hope that's accurate.
We are happy to get funding.
Okay, thank you, Martin, Reshma, and Victor, and everyone who has attended today. This was a great webinar, and working with ABC as part of this SETTN project. I'm very pleased to say that this definitely shows a way forward for TANGETCO to overcome a lot of its current challenges and move into the future. One is it talks about the importance of demand side measures and storage, and Martin correctly mentioned that we are a little late in starting to implement these solutions. We are seeing how consumer side solutions can help in a lot of things, more loss reduction being one of them, but at the same time you also saw the drastic improvement in power quality that you're able to get, especially on the voltage control front. Similarly, with these active inverters, I'm sure harmonic controls also should be something which would be in the realm of power quality control. The only hope is that the utility sees these as sees these savings and starts to bring in changes in its business models and approach towards how to engage consumers. And this is actually giving a lot more voice to the consumers to have their own energy systems, interact with the utility, and make it much more of a democratic grid, so to say. So we can hope and try to work with the agencies and consumers within the state and see that we achieve the stated clean energy goals. So that said, I wanted to thank everyone for taking your time out and for your interest in this webinar. The registered participants will get an email with the presentation and a report along with it. So I'm not sure whether it will be an attachment or a link. I'll request Victor or Martin to clarify. And I'm also, there is a short feedback form which is going to be popped up at the, towards the end of this. I think it will be a voting pattern on your Zoom screen itself. So Niveda, you could take that up and please project the votes.
Thank you, Deepak.
Thank you everyone, and stay safe. Goodbye.
Thank you, Reshma.
Thank you all.